Find the indefinite integrals. In this video, there are just a couple more examples of how to find an indefinite integration with some rewriting so that we can use the power rule. In the first example, we have the indefinite integral of x to the fourth power plus the square root of x dx. Now, one thing I want to point out before we go much further is if you are taking and finding an indefinite or even a definite integral later of a function with more than one term, you will need to have parentheses around the entire expression that encapsulate all of the terms. This is what allows us to use the sum and difference rule, and in this case we will use the sum rule. Over here we can use the difference rule. It just allows us to do the following. It allows us to look at this as x to the fourth power dx plus, and that plus comes from right here, x to the, rewrite this, the indefinite integral of square root of x will be x to the 1/2 power dx. So now we can use the power rule, and I'm going to use two different colors here. I'll do the first indefinite integral in yellow and the second one in blue. So with the power rule for indefinite integration, it tells us to add 1 to the exponent, then multiply the front by the reciprocal of the new exponent. And I said I wanted to do that in yellow, so I'll do that here. 5x to the 5th power. All right. The second indefinite integral tells us that we need to add 1 to the new exponent, so that'll be 3 over 2, and we multiply by the reciprocal out front of the new exponent. So 3 over 2, the reciprocal is 2 over 3, that gives us this new coefficient here. And the all-important plus c. Do not forget that. And this is the answer. If you take the derivative of this answer, you'll end up with what we got in the integrand. For this next example, let me section this off here. For the next example, we will have to do some rewriting. So this first term becomes x to the negative 2/3 power minus 4x squared dx. And that is because if you rewrite this radical notation as a rational exponent, this will be 1 over x to the 2/3 power. And then if you bump it up to the numerator, it becomes x to the negative 2/3 power. So now we can separate this out into two different indefinite integrals. So the indefinite integral of x to the negative 2/3 power dx minus the indefinite integral of 4x squared dx. And again, since there's only one term in each of these integrals, we do not need these parentheses anymore. Only when two or more terms show up in this indefinite integral. So now we can use the power rule. And the power rule, again, I'm going to use two different colors here. We'll do the first indefinite integral in white and the second one in blue. And I know already that this minus sign is going to come along for the ride. So there it is. Now with the indefinite integral here in the first term, the first thing we need to do again by power rule is add 1 to the exponent. So this will be x to the 1/3 power, and then in front of that we need to multiply by the reciprocal of the new exponent. So the reciprocal of 1/3 is 3. In the second integral over here, the x is being squared, so I need to add 1 to that exponent, so that'll give me x to the 3rd power. In fact, that constant comes along for the ride. And then I need to multiply all of this by the reciprocal of the new exponent. So the reciprocal of 3 is 1/3, and then out back, the all-important plus c. So Now there's just a little bit of simplification that needs to happen, and this ends up being 3x to the 1/3 power minus 4 times 1/3 gives you 4/3 x cubed plus c. So here is the final answer. Let me put my equal signs in here. There we go. So this 3x to the 1/3 power minus 4/3 x cubed plus c is the indefinite integral of what we started with. And again, you can check your work by taking the derivative of your final answer and see if you get what is on the inside or of the integral, or we call the integrand. Find the following antiderivatives. In the left example, you'll see that you are trying to find an antiderivative of the quantity a squared minus 2 times the quantity a plus 7 with respect to a. Now, in its current form, we cannot find the antiderivative of this expression. Since we only understand power rule at this point in time, we need to be able to use a power rule here. There's no trigonometric expressions here, so we need to use the power rule. And in order to get something that will give us power rule, we need to distribute these two expressions to one another. And when you do that, you'll see that you get the antiderivative of a cubed plus 7a squared minus 2a minus 14 with respect to a. And from here we can use the power rule to find the antiderivative. So I'm going to just look at each term individually. This first term, a to the 3rd power. A to the 3rd power, when you use the power rule, tells you to add 1 to the exponent, so a to the 4th, and you multiply that times the reciprocal of the new exponent. Plus, I'm going to do 7a squared, so I'm going to have 7a, add 1 to the exponent, so 2 plus 1 is 3. Multiply this term by the reciprocal of the new exponent. This next term, minus 2a, so minus 2a, add 1 to the exponent, multiply by the reciprocal of the exponent. And the last term over here, minus 14, will turn into minus 14a. There's an a to the 0 power hidden in here. So when you add 1 to the exponent, you get a to the 1st power. And then lastly, we cannot forget plus c. So now that we have an expression here, we should probably just go ahead and simplify anything that we can. So I'm going to rewrite this as 1/4 a to the 4th power plus 7/3 a cubed minus a squared minus 14a plus c. And here's an answer for the antiderivative of the first example. In this right example, we cannot use a power rule yet because we don't have separated terms like we did over here in this example. But we can get separated terms if we take the denominator and divide each term of the numerator by it separately, so that it'll look something like this. The antiderivative of x cubed over x cubed minus 7x over x cubed plus 2 over x cubed, all with respect to x. Then what we can do is simplify each of these terms into something like this. So the integral, or the antiderivative of 1 minus 7 over x squared plus 2 over x cubed dx. Then what we need to do is we need to make sure that all of these x's in the denominator get bumped up to the numerator. So the last rewrite that we will need will be the integral of 1 minus 7x to the negative 2 power plus 2x to the negative 3 power dx. Now we can go ahead and find the antiderivative for each term. So when we do this, we're taking the antiderivative with respect to x. So when I find the antiderivative of 1, it will end up having a variable x. The next term, minus 7x to the negative 2 power, this will be minus 7x. If you add 1 to negative 2, it becomes negative 1. Multiply by the reciprocal of the new power. To that, I'm going to add this one, 2 times x, add 1 to negative 3, you get negative 2, to the 1 over negative 2 power. And then, of course, at the very end, plus c. Finally, all we need to do is simplify our numbers. So x subtracting a negative 1 is the same thing as adding 7x to the negative 1 power. 2 and negative 2 will reduce so that this becomes minus x to the negative 2 power. And then lastly, since there are negative exponents here, we need to get rid of those as well. So this will leave us with x plus 7 over x minus 1 over x squared plus c. Please do not forget your plus c's at the end of these antiderivatives. Here is your answer for this antiderivative. Find the following antiderivatives. In this left example, we'll be finding the antiderivative of secant squared x minus 4 cosecant squared x dx. And in order to figure out these antiderivatives, it's almost like a memorization. You'll have to remember that the integral or the antiderivative of secant squared x dx is tangent of x plus c, and that the integral of cosecant squared x dx is negative cotangent x plus c. So when you look at this antiderivative up here, the antiderivative of secant squared is tangent of x, so I'll write my answer down here in red. This will be tangent of x minus 4 times the antiderivative of cosecant squared is negative cotangent x. And don't forget to add the all-important plus c. So now the only thing that needs to happen is that with these signs here, the negative 4 times the negative cotangent just need to be multiplied so that you can see the final answer is the tangent of x plus 4 cotangent x plus c. And if you'd like to check your answer, you can always go back and take the derivative of this answer. And just remember that c is a constant, so the derivative of this last term will just go to 0. And the derivative of tangent is secant squared, and the derivative of cotangent is negative cosecant squared. So this looks like it checks out. All right, in this next example over here on the right, cosecant theta times cotangent theta minus cosecant theta with respect to theta. We need to find this antiderivative. Well, in its current form, we do not know an antiderivative for cosecant or cotangent. However, if you distribute the cosecant to both terms on the inside, you'll see that you get something like this. So this antiderivative will equal cosecant theta cotangent theta minus cosecant squared theta d theta. From here, you should recall that the antiderivative of cosecant theta cotangent theta d theta is equal to negative cosecant theta plus c, and that the antiderivative for cosecant squared is over here already in this example. So now we can take the antiderivative of each term. So this first term, cosecant cotheta, when you find the antiderivative of that, you'll just get negative cosecant theta. So this will equal negative cosecant of theta. And the second term over here we've already used in this other example. That should give us minus a negative cotangent theta, all plus c. So the final answer over here, after simplifying, subtracting a negative, will end up being negative cosecant theta plus cotangent theta plus c. Find the function f given the derivative and the initial condition. The derivative is f prime of x equals 4x to the fourth power minus sine of x. The initial condition is over here, f of 0 equals 5. So in order to find the original function given the derivative is to go ahead and find the antiderivative of this function. And in order to do that, you need to find the antiderivative of 4x to the fourth power minus sine x, all with respect to x. So going through and figuring out this antiderivative, I know I'm going to have 4x to the fourth power, except it's not going to be the fourth power. I'm going to add 1 to that exponent. And then out front, I'm going to multiply this entire term by the reciprocal of this new exponent. And for the antiderivative of sine, I know that it is going to be negative cosine of x. This is just one of those trig antiderivatives that you will have to memorize. And then at the very end, I have to add c. So simplifying this down a little bit, I know I'm going to have 4/5 x to the fifth power plus the cosine of x plus c. And in previous examples and exercises, you may have noticed that this plus c is just kind of here. We don't know what it is. If we take the derivative of it, we know that this will be 0. And if you take the derivative of all of this other stuff, you'll end up with what we started with in our derivative. But we cannot write anything but plus c because we don't know what number it is supposed to be. That is where this extra bit of information will help us. So I should finish this last line here. This is our f of x. This is our original function. If we take the derivative of this thing, we'll get what we started with. So now we have some information. If you substitute 0 in for x, here, 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 we should get back a y value of 5. So let's set this up. So I know that f of 0 is equal to, well, just the function if you substitute in 0 for x. Plus c. But I also know that f of 0 is also equal to 5. So I can set this entire expression equal to 5, and now c is the only variable in this entire equation. So now we can solve for c. It turns out this first term here is 0 plus this next term here, cosine of 0 is 1 plus c, we know will equal 5. And when you solve this for c, c will be equal to 4. Now we're almost done. The directions state to find the function f. Well, we found most of the function. We also found a c value. The last step here is to make sure you substitute that c value back in there for a final answer of f of x equals 4/5 x to the 5th power plus cosine of x plus 4. So here's our completed final function of f of x given a derivative and an initial condition. Find the function f given the derivative and the initial condition. So in this case, we will not actually be wanting to find the function f. We will want to be finding the function y, since we're given a y notation here. So what we need to do first in order to get back to an original function is we need to find an antiderivative of this function. So if you just concentrate on the right side here, we just need to find the antiderivative of cosine of x with respect to x. And when you do that, you'll notice that you get the sine of x plus c. And since when you're finding an antiderivative, you're going backward one step, this means that what we just found right here will go backward one step from a second derivative, so that means we will have found the first derivative. So y prime equals sine of x plus c. Now, this notation over here doesn't get used too frequently, but this means if you substitute pi over 2 into the first derivative, you'll get back a positive 2. So, looking at that, if we evaluate this derivative, y prime of pi over 2 equals the sine of pi over 2 plus c. That's what y prime of pi over 2 means. But this is also equal to 2. So now that we have this equation here, we can solve it for c. So in order to solve this equation for c, you need to know that sine of pi over 2 is in fact 1 plus c equals 2. And that will lead you to the conclusion that c equals 1. So that's good, except you can't just have a first derivative with a c and then find out this little bit of information about c and then not do anything with it. We need to substitute this one back into the first derivative. So our first derivative now becomes y prime equals the sine of x plus 1. This c value got substituted in. All right, so we're still not back to the original function. We have done some work to go from a second derivative to a specific first derivative using this information. But we need to go back and actually find out what is y, what y is equal to. So again, we have to figure out the antiderivative of this bit. And I'm going to do that over here. So the antiderivative of sine of x plus 1 with respect to x ends up being negative cosine of x plus c. And much like we did over here with the y prime, after we figured out the antiderivative, which is the opposite of differentiation, we're going backward. We found it. We had a second derivative, moved to a first derivative. Now that we repeated the process again, it's almost like we're just taking away these derivative signs one at a time. So over here, this is the function y, except we still have this plus c hanging around. We need to get rid of that. So back up here to this information, y of pi over 2 is 3 pi. So what that means is if we know y of pi over 2, that is the same thing as writing negative cosine of pi over 2 plus pi over 2 plus c equals 3 pi. And when you go through and simplify this equation over here, you'll see that the cosine, the negative cosine of pi over 2 is 0, plus pi over 2 is just pi over 2, plus c equals 3 pi. And when you solve this for c, by subtracting pi over 2 from both sides, c is 5 pi over 2. And again, we cannot just stop here. Now, we found a specific c value, yes, but we're trying to find a function. So this c value needs to get substituted back up into the original function. So we'll have a final answer of y equals negative cosine of x plus 5 pi over 2. And there's your answer for the initial condition exercise.